transmitter hardware model. So what jobs need to happen in the transmitter? So basically we have some message to send. So let's say it's a picture or an audio file or something of that nature. The first task that needs to take place is encoding. What do I mean by encoding? So this is a message incoming here. By encoding, I mean all of the tasks that are necessary to prepare the information to be transmitted. So this could start out as some form of digital information. It could be, for example, ASCII. It could be executable code, but it might not be in the precise binary format that we want. So the encoder then will take this message, even though it's digital, and transform it into a string of ones and zeros, or whatever symbols we need. If the message starts out as something analog, let's say a JPEG or something like that, the encoding starts out as an image, the encoding would do something like JPEG compression and transform it into, again, a sequence of ones and zeros. Okay, so now that we have our binary signal, and again, it need not be binary, we'll talk about generalizations of that. Next step is modulation. So the modulator. This is a vector, 0, 1 to the n. By that I mean an n-fold vector of binary bits. The modulator basically takes 0 and maps it into some continuous function representing a 0. And it takes a 1 and also transforms it into a continuous function representing a 0. Best way to think about this so far is all in the digital domain. So in other words, 0, 1, and basically I replace it with a sequence of samples. Okay, next step, as far as the transmitter is concerned, is, so this is now some discrete function of time. Actually, excuse me, let's do this. My notation will be as follows. If a function is discrete time, the argument will be in square brackets. And I will usually use k instead of t. And if it's continuous time, it'll be in round brackets. So basically, that's just a vector. Okay, from the modulator, we go to digital to analog conversion. And from that, we get some function of time, so continuous value function of time. We then amplify. And we go to physical, what I'll call physical layer access. Okay, physical layer access, that'll depend on the medium that's in use. The physical layer access, if this is a copper wire, then this is just basically the wire in, or some impedance matched end of the wire. If this is a wireless channel, then the physical layer access would basically be an antenna and an antenna assembly, and whatever analog modulation is needed to access it. In this course, we are basically concerned with everything over here. So everything over here is discrete time and implementable in software. Everything over here is continuous time. For hardware. So this is the side of this problem that we're most interested in. Similarly, at the receiver, does everybody have this? Here is the receiver hardware model. it's sort of exactly the same thing in reverse with a couple of extras. So here's physical layer access. So this is the module that, again, interfaces with the medium and basically gives you the signal. Coming out of that, the signal is weak, so let's amplify it. An unavoidable feature of the amplifier is noise. We didn't see this at the transmitter because at the transmitter, the signals were already relatively powerful and washed out all the noise that was introduced. So usually we only talk about noise being added at the receiver, because here the signal is extremely weak and is comparable to the random motions of electrons in the amplifier, which is the source of the noise. Usually noise is additive, so it's added on top of whatever signal comes out of the channel. So here we have some FMT. It comes out amplified. Let's call that. Let's call this F prime T. Of the amplifier, it's FMT is the scaled version of F prime T. We add the noise, and we get F of T plus N of T. Called the noise N of T. And then we hit analog to digital. At the output of analog to digital, we have samples F of K of the signal and N of K of the noise. We pass that along to demodulation. Demodulation is the signal processing that's required to take this distorted signal and transform it into binary bits. So basically here we're making this, we look at these signals and say, what was sent, is it a 1 or a 0? That decision is taken here. So at the output of demodulation, we have a sequence of binary bits. And finally, decoding. So hopefully, these bits that are detected by the demodulator are the same as the bits that were detected by the modulator, and here you have the same message. If you've done your job properly, then you have the same message at the output over there as you did at the input. So once again, everything on this side is continuous time and hardware oriented. Everything on this side is discrete time and software oriented. So we're going to turn our attention to basically everything over here. So our job, which is actually fairly considerable already, is to design basically the modulator, the encoding, the modulator, the demodulator, and the